Hi everyone, welcome back to Calc 3, and now we're going to start section 16.2, so we're jumping ahead in the book. And remember, chapter 16 contains more difficult concepts, but it's really the more interesting concepts, what all of the things that we're learning in the previous chapters are leading up to. So we talked about line integrals before break, and all of these changes happened. And we talked about line integrals of multivariable functions. So today we're going to talk about line integrals of vector fields. So before we can talk about the line integrals themselves, we need to define what a vector field is. It's another kind of function that we haven't talked much about. So we talked about scalar functions. Those are functions that take in points. They can be single variable or multivariable. So single variable scalar functions, you talked about Calc 1, Calc 2, every other math class that you've taken for years and years. Multivariable scalar functions, those are what we were introduced to at the beginning of chapter 14. They take in multiple numbers, and the output is a single number. In chapter 13, we talked about vector functions of a single variable, where you have some parameter t. That's the input, and the output is a vector. Well, vector fields are kind of like multivariable vector functions. So the input are points, so now just not a single parameter, but points xy or xyz or however many coordinates you have, and the output is a vector. And we always keep the same number of variables equal to the size of the vector. So for instance, if I have a two-dimensional vector field, that means I have a function of two variables, x and y, and the output is a 2D vector. So I have one component, two component. And both of these, this p and q, these are multivariable scalar functions, so what we've dealt with in chapter 14. In 3 dimensions, my vector field is a function of 3 variables, x, y, and z, and the output is a 3-component function. Now all of these p, q's, and r's, these are functions of 2 variables, these are functions of 3 variables, those are called component functions. It's the same thing that we had in chapter 13, it's just in chapter 13, these were all functions of 1 variable, now they're multivariable functions. So each one of these, the input, you have multiple variables going in, and the output is a single number, so that when you put these together, you get a vector. Okay. Now, sometimes to clean up notation, instead of writing f of xy or f of xyz, you just write f of vector x. So here, x is a vector. It could be a vector of any number of components. So here it's a vector of 3 components, but this could also be just x, y, or could be a vector of 4 components, 5 components, as many components as you want. And this just makes the notation the same, no matter how many dimensions you're dealing in. But the important thing here is for a vector function, you can, or a vector field rather, you can think of these as vectors coming in, vectors coming out. Or you can think of them as points going in, multiple variables going in, vectors coming out. Okay? A couple quick properties about vector fields. Vector fields are continuous if and only if the component functions are continuous, meaning that if we'll just look at the 3-dimensional case right now, if p, q, and r are all continuous functions, then f is a continuous function, continuous vector field. And if f is a continuous vector field, then that means all 3 p, q, and r have to be continuous. It works both ways. Same thing for differentiability. Vector fields are differentiable if and only if the component functions are differentiable, meaning that they have the partial derivatives exist, and they're continuous on an open region containing the domain. Now, what do these things look like graphically? If we want to graph a vector field, then you take any point in the domain, and on top of that point, you draw a vector. So basically what you're seeing, let's look at an example while I explain this. For a vector field, the graph of a vector field, you're seeing the input and output of that function at the same time. So let's say, here's an example, here's a vector field of 2x, 2y. So that means for every point I have, let's say I have the point 1, 1, I plug 1 in for x, I plug in 1 in for y, I get out the vector 2, 2. And this is exactly what you graph. This point 1, 1 was the input, and then starting at that input value, I draw the vector, that's the output. So the vector starts at the input value. So this is the vector 2, 2. Now this plot isn't drawn to scale, but just to get the idea, here's another example. Here's another point 0, negative 1. If I plug 0, negative 1 into my vector field, I get the vector 0, negative 2, because I plug in 0 for x, negative 1 for y. And so if I wanted to draw this vector, I put a vector starting at that point going straight down 2 units. That's the vector 0, negative 2. Now if I wanted to plot this vector field, right, this graph isn't an entire plot of this vector field. I would have to plot a vector at every point. So every point in the plane gets assigned a vector. Now, practically we can't do that, right? I can't fill the plane with infinitely many vectors. But if we go to Mathematica for a second, what we could do is pick some representative vectors, or representative points. So for instance here, this is the same vector field, 2x, 2y. Some points in the plane have been picked, so not every single point has been, a vector has been drawn at every single point, but a representative of points in the plane to get an idea of what the vector field looks like. And the size of the vector here isn't exactly the correct size, but they're drawn proportional to their length, right? So as we get closer and closer to the origin, these vectors, the magnitudes are smaller because that's what happens with our vector field. As we get away from the origin, the magnitude of the vectors get larger. And at the origin itself, if I plug in 0, 0, I get the 0 vector, so there's nothing there. And so that's a vector field plotted there in 2D. It's a two-dimensional vector field. Now if I look at another example, which we have here, this is the vector field negative y over the square root of x squared plus y squared. That's the first component. The second component of the vector field is x over the square root of x squared plus y squared. And now I see that I get this kind of circular vector field, right? So at each point, you draw a vector that represents this vector field. Here you have a representative of points. And you'll notice that instead of a plot what we had in the first example where I have some small vectors, some large vectors, here all of the vectors are the same size. That's because the vectors for this vector field, negative y over the square root of x squared plus y squared, x over the square root of x squared plus y squared, these are all unit vectors. If you take the magnitude of this vector field, you'll always get 1, no matter what you plug in for x and y. So all of these vectors have magnitude 1. The origin was not one of the points that got used here because this vector field is not defined at the origin. So these are a couple of examples of two-dimensional vector fields. When you go to 3 dimensions, it's more difficult to visualize these things, but we'll try a couple of examples. Here's a constant vector field. So this vector field is the constant 1, 0, 3, which means at every single point in space, every x, y, z value, I'm going to plot the vector 1, 0, 3. So all of these vectors that are plotted here are exactly the same. And if I start lining up the direction, you can see they all look the same down the line. If I look in this direction, they look like they're going straight up. Now the reason they look like they're going straight up is because right now I'm looking down the x direction, I'm looking across the y direction. These vectors don't move in the y direction at all. They're 0 in the y direction, so that's why they look like they're going straight up. If I look here, it looks like they're going to the right and up because the x component is 1. So they're going 1 in the x direction, 3 in the z direction, 0 in the y direction. Another example of a 3-dimensional vector field. Here I've plotted 0, 0, x. So now this vector field only has a non-zero z component, which means all of these vectors are either pointing up or pointing down. And that's exactly what we see. Now we're looking down, pretty much looking down the y-axis, looking in the x direction, so we can see that the magnitude changes as we change x. And that's exactly what's happening because our third component is x. So how large our vector is going in the z direction depends on the x coordinate. So as x gets closer and closer to 0, the vectors are getting smaller. If x is negative, the vectors are pointed downward. If x is positive, the vectors are pointing upward. If I look down the x direction, it's more difficult to see anything, because now I'm looking at how things are changing in y. And in y, everything's uniform, so it's hard to see anything. If I look down the z-axis, I just see things, vectors either coming towards me or going away from me. So things are much more difficult to visualize in 3 dimensions, but 3-dimensional vector fields do exist. Go back to our notes. We'll finish this video by talking about different types of vector fields. So one type of vector field that we're going to talk about are called velocity fields, and these describe the motion of systems of particles. So you can think that we talked about these parabolic paths of projectiles. You would have a velocity field describing the velocity of the projectile as it moves. We're usually going to use these for fluid flow or air flow. We also have gravitational fields, and these are defined using Newton's law of gravitation. I don't know how often we're going to use this, but just as a couple of examples of what you can do here, this vector field is very specifically defined. F of x is negative lowercase m times capital M times g over the magnitude of x cubed times x, where x is a 3-dimensional vector. Capital M is the mass of an object located at the origin, 0, 0, 0. Lowercase m is the mass of an object located at x, y, z. So that's your input vector, is pointing to where this other object is located. G is some gravitational constant, and the output tells you the gravitational force between the two objects. Okay. There's also electric force fields, defined by Coulomb's law, and it looks pretty similar. Here we have some epsilon lowercase q capital Q over the magnitude of x cubed times x, where again x is a 3-dimensional vector. Epsilon is some constant that changes depending on what units you're using to describe your electric force field. Capital Q is the electric charge of a particle at the origin. Lowercase q is the electric charge of a particle located at xyz, where your input is pointing. And F tells you the force exerted on the particle at xyz by the particle located at the origin. Now both of these vector fields look similar, and they can both be described in the same way as inverse square fields. In inverse square fields, you might say, why is it inverse square if we're dividing by the magnitude cubed? Well, it's called inverse square because we think of the input as a unit vector, and then we have some constant being divided by the magnitude squared. So if I think of my input as a unit vector, and I'm dividing by the magnitude squared, then what I really get is the magnitude cubed in the denominator. And so you can see that both of these examples fit this format of an inverse square field. In the first example, k is actually negative lowercase m times g. That's my constant. And in the second example, my constant is epsilon times q. Those will both be my k's. Vector fields aren't exactly new to us. We've talked about a particular kind of vector field in a couple lessons ago. Gradients are vector fields. So if I have a differentiable function and I take the gradient of that differentiable function, that's a gradient field, right? It's a vector of partial derivatives. Now mostly we were using these gradients at a specific point, so they were fixed, but we can let these things be functions. So I just let x and y, or x, y, and z be variables. I get a vector field. And the gradient vector field contains the partial derivatives of some differentiable function. So that's it for now. In the next video, we'll start taking some line integrals.